Hello everyone. Our team is from Kuaishou Technology, and I feel honored to be able to participate in this discussion group to share our experience on Mahjong AI. Our Mahjong AI, named Mahjong Master, is a general Mahjong AI system. We not only use it for this Chinese standard Mahjong AI competition, but also apply it to many other types of Mahjong, and it's already online at Kuaishou's Mahjong game called Doulai Wan Mahjong. So today I will not only talk about our AI in this competition, but also how we build this general framework which we use to train intelligent agents in different types of Mahjong rules. Before we start, I'd like to introduce our team. Our team members are from two departments in Kuaishou, AI Platform and Game Business Department. And what we do is basically using AI to empower, to support, and to optimize the whole process of games in Kuaishou. We use AI in many different stages. For example, in game development stage, we use AI to do automatic test and level generation. To promote new games, we build an intelligent advertising system to promote our games and advertising platforms. To support operation of a game, we develop data-driven strategies for game matching, novice protection, and so on. For Game AI, we have a Game AI platform which we can use to train AI for many different games in Kuaishou, like Mahjong and Find Landlord, and so on. We have already applied these techniques in many games in Kuaishou, and the strategies given by AI outperforms those given by humans. Okay, let's begin our presentation. This presentation consists of two parts. The first part is an overview of our AI system, including why our system is general and how we make it by designing certain decision-making method and feature and model structure. And the second part is how we train our Mahjong Master, including a distributed deep reinforcement learning framework, and some details like how we initialize our RL model and other training techniques. Firstly, we are going to show why our system is a general Mahjong AI system. An AI system based on reinforcement learning basically consists of three parts: the environment, the training system, and an agent. Our system is general because we have generalized the algorithm for different Mahjong rules. We have the same training and inference framework and the agent design. The only different thing is the environment, which is rule specified. So if we want to extend our system to a new Mahjong rule, we just need to change the simulator and use the same agent and training system and we can easily get a new Mahjong AI. So actually, we have already applied our system in online Mahjong games. We serve more than 6 popular types of Mahjong rules, and according to online data from Doulai Wan Mahjong, our AI has surpassed the top human players. And in this competition, we ranked first place in the tournament round and third place in the final round. Then let's talk about an important design to make our AI a general system: our one-step decision-making method. A traditional way for Mahjong AI to make decision is such a kind of decision flow, which we see from MSRA's paper Suffix. Suffix learns 5 different models to handle different situations, and each model only decides one type of action. This kind of method is straightforward because it is similar to the way that human players make decisions. However, it's not the most suitable way for a general Mahjong AI system because the decision flow is rule-specific and each model is specialized to only one action. If we change to a new Mahjong rule, we need to change our decision flow, and we need to train many different models, which is not very convenient. So what we use here is our one-step decision-making method, in which we only use one model to make all types of decisions. In each different situation, we just generate all the available actions in this situation and the observations of the stage, and change it to features and pass it to the model. And the model in one step will tell us which action to choose. So this type of decision-making method is very suitable for reinforcement learning training, and it's easy to extend to different type of rules because only one model needs to be retrained. And it also has low cost for training and inference. And this method is very important in our general Mahjong AI system. And another important thing is our feature and model structure. As mentioned in MSRA's paper, convolutional neural networks have demonstrated powerful representation capability on the dimension of tiles. So we also adopt the convolutional neural networks and the ResNet to extract our features. However, there are some features that are not related to certain tiles, and the convolution on these features become nonsense. So we decide to split the feature into two parts. One is the tile-based features, which includes the hand tiles and the tile set, and other features including the dealer position and available actions, which are not related to the tiles. So the first tile-based features, we go through a ResNet to extract features and then flatten it and concat with the other features, which goes through an MLP. And finally, they go through another MLP to generate the final action, which is one-hot encoding. From our experience, this model fits well for all types of rules, as long as the feature design is reasonable. And we apply it to many different types of rules, including Chinese standard Mahjong, Sichuan Mahjong, and two-player Mahjong, and so on. Okay, now we are going to talk about the second part, the training of our Mahjong master. Firstly, I want to introduce our distributed deep reinforcement learning framework. It is quite a classical framework and is similar to the framework in MSRA's paper. It has self-play workers and a parameter server, and it uses async training and simulation and deployed on multiple CPU and GPU machines. But we make many adaptations and optimizations to make our system run faster. We use the batch inference to greatly increase the inference speed. And in the sync process, we use the broadcasting to make the sync more quickly. And we also support many different reinforcement learning algorithms, which is convenient for us to train many different Mahjong rules and other kind of games. So with this framework, in this competition, we can simulate 48 games per second per GPU card in the inference engine, and it is 20 more times faster than the training framework described in MSRA's paper Suffix. So with this framework, we can easily extend our AI system to many different type of Mahjong rules. The second thing we want to share is our model initialization method. In practical reinforcement learning from random policy is always very hard, so the good initialization of the model is important. A common way for it is that we use the human expert data to supervise the model and then use the model to reinforcement learning. However, in some situations, we find that we don't have access to the expert data or even any type of human data. So what we do is we develop a method called the rule-based initialization. First, we write a rule-based AI and then use it to generate the supervised learning data. And we use this supervised learning data to supervise a model, and then we go to the IL process. In practice, this rule-based AI don't need to be very high level, and it will perform well when we go through this process. So these two method both performs very well, and we just need to choose the suitable way to do it according to the different situations. And these two methods helps us a lot to extend easily from different rules. Finally, I want to share some other techniques that we use to train our Mahjong AI. First is the reward design. It consists of two parts. The first part is we use some handcrafted reward to avoid sparse reward, and it turns out to be very useful for the early training process. And the second one is that we adapt the duplicate format and use the difference between the player's scores as the reward instead of the raw scores, and it turns out can reduce the variance of the reward. And the second thing is the entropy control. We use a similar format to the MSRS paper, in which we use a control parameter alpha to control the entropy of the policy close to a target policy. And after a certain time, and we gradually decay alpha to 0 to ensure that our policy can converge and get rid of the entropy control. And the third thing is oracle guiding. The idea is similar to MSRS paper, but here we train as oracle model and then decay to the normal model. But here we use the distillation to decay instead of masking, which is described in the MSRS paper. Okay, that's all the thing that I want to share today in this seminar, and I want to thank you for your patience of listening to my speech. And if you have any questions, please feel free to contact us via this email. And thank you very much. Goodbye.